It's my pleasure to introduce Latham Boyle. We'll give, I'm not sure if it's the first in a series, which will be continued by Shane, but if they're connected in any case, which will be the standard model as a differential graded superalgebra.
Thank you, Walter. So let me first say thanks so much to Walter and Simon and the organizers for organizing this. It's really nice thing. Okay, so I'm going to tell you about. This is work with Shane Farnsworth. We've been working on it a long time. The paper, we finally finished it this weekend, so it's actually coming out in the archive tonight, which is kind of good because I didn't really sleep on the plane 2 nights ago over here, and then because of jet lag, I didn't really sleep last night either. So I'm barely coherent, really. So. Anyway, I hope even if you can't understand a word of what I say, if I mix it all up, then still have a look at the paper. I think it's worth looking at. Okay, yeah. So. Okay, so in brief, what I want to explain is this idea that, what this paper is about the idea that there is a sense in which the normal data in the sort of traditional spectral triple formulation of non-commutative geometry, this data that we know and love, it kind of naturally sews itself together into a certain superalgebra. So that we're here. I've noticed that I'm writing the algebra that usually appears in the spectral triple as A hat, sort of the algebra of coordinates, if you will. And where here A with no hat will mean the algebra of forms over A hat. So there's this. So the idea is that there's this. There's the superalgebra here, and the simple requirement that this thing be a differential graded star algebra or star DGA really turns out to perfectly capture nearly all of the structure of the standard set of axioms and assumptions of non-commutative geometry. So in other words, this really, when you unpack it on this algebra, is really tons of conditions actually. But every one of them, as you go through, it's all an axiom or assumption that you either know you're making, or maybe one that you don't even usually think about that you're making when you work with normal non-commutative geometry. But then, so this is like gets back non-commutative geometry, I want to say. But then there's plus additional constraints. Okay, there's a bunch of extra constraints you get that are new. So then I want to say that if you then take the traditional non-commutative geometry used to describe the standard model, the traditional spectral triple, and you plug it into this formula, and you look at what these extra constraints say, it's great. They all are physically meaningful and phenomenologically correct. Okay, so that's what I want to. That's basically what I want to flesh out. I want to, as I say, I'll only be able to get I'll only be able to get to a little bit of this. There's a paper on the archive tonight with all the details if you're interested, and then Shane will be covering some different aspects tomorrow. That I won't have time to get to, but I just want to explain the idea here. So now let me say, so this proposal is really very similar to a previous proposal that Shane and I made in 2014. If you want, there's only one little change, which is that back then we took the algebra of forms to be represented on the Hilbert space of the fermionic Hilbert space in a too naive way. Now we take an appropriately graded representation. And we take basically the simplest possible graded representation. I'll explain in a minute. But but that really makes all the difference. It's a gigantic improvement. And so let me pause to say that, our previous formalism had some of the advantages that this new one does, but it also had two problems. And there was a very good follow-up paper to our work by Bruder and Beasy and Besnard, who I don't know how many of those people are here. I know Beasy. I know Nadir is here somewhere, or I saw him outside. There's Nadir. Yeah. Oh, okay. Yeah. So they wrote this great paper, and basically what they with our old way of doing things, when we took an ungraded representation of A on H, there were two problems. First of all, A was a differential graded algebra, but it was unpleasant that B was not in the previous way we were doing things. And that was because of the presence of extra so-called junk forms that weren't eliminated in our way of doing things. And then the second thing is that, as I'll explain, some of these additional constraints we get. So in non-commutative geometry, you have the order 0 constraint and the order 1 constraint. And then in this way of doing things, you also get an order 2 constraint. And in our previous way of doing things, the order 2 constraint, when you applied it to the finite part of the standard model geometry, so the standard model geometry is a product of a continuous part, sort of a continuous 4-dimensional manifold, and a finite part, like a discrete non-commutative 6-dimensional space. And when you applied this order 2 condition to the finite space, it worked great. It eliminated terms that you wanted to eliminate in the first place, that previously you had to use this so-called massless photon condition to eliminate them, but then they were instead eliminated by the order 2 constraint. So that was good. But then when you applied this order 2 constraint to the continuous space, to the 4-dimensional geometry, it was too strong. It was incompatible with that. And so that was bad. So there were those two problems, and Bruder et al. Pointed out that the key to solving those was that those were both simultaneously solved if you switched to taking an appropriately graded representation of A on H. And they had this particular proposal for a graded representation of A on H where, well, I won't get into that. I think maybe Nadir, I'm not sure if he will or won't discuss it. But anyway, so we want to propose a different. So the key idea we keep, which is that the resolution is to take an appropriately graded representation. But we're going to do something more minimal, which is just to take nothing more than what was already there. So we had a Hilbert space here, but it already was equipped with a grading, which splits it into a grading gamma, which splits it into a left and right-handed component. And we're going to say that these are the only two graded components of H. And the only new thing is just to say that that grading is exactly the same as that grading. That is to say, they interact with one another so as to make this whole algebra a compatible graded algebra. Okay, and so that if you want, is the kernel of everything. And it turns out that if you make that one simple change, that a lot of nice things fall into place. But before I can explain how that works, let me just go back and say a simple point about. Okay, so the basic idea is going to be to define this algebra, and then demand that it satisfy the properties of a differential graded star algebra. So let's just talk for a moment about what are the properties of a differential graded star algebra, because everybody knows what the properties of differential graded algebra are and what the properties of a star algebra are. But there's just one point that at least we weren't familiar with that arises when you combine the two things. But that's going to be key for getting this all to work. So what is that? So okay, so differential graded algebra, the fact that it's graded, let's say A is our differential graded algebra. The fact that it's graded means it's the direct sum of some graded components, so that if you take an m form from the mth component and times an n form from the nth component, you get an element of, you get an m plus n form. And then the differential part is saying that this algebra is equipped with some operator d that's of order 1, so it maps you from m forms to m plus 1 forms, and it's nilpotent. And it satisfies a graded Leibniz condition. So if you act on the product of an m and n form, you get okay, and then the fact that it's a star algebra, that's saying that if you take the star of an m form times an n form, you get the n form star times the m form star. And then also that if you take the star twice on any object, that you get back the object. Okay, well, actually, I'm going to write you get back the object times epsilon, which is a plus or minus sign. In a normal in a normal DGA, you can prove that epsilon has to be 1 from these other requirements. But it'll turn out that when you have, so here, if we start with a star algebra here, the differential graded star algebra here, and then we take this sort of order 0 extension, this sort of extension where this thing is a, we've extended this guy by a component that squares to 0, then on that component, turns out epsilon can be either plus or minus 1. And I'm calling it epsilon because this sign here, this sign choice on that null component is just going to be exactly the epsilon that normally appears in non-commutative geometry, this choice j squared equals epsilon. But then the last thing, well, maybe I'll write it over here. The last thing I want to say is that, so the one thing we haven't discussed yet is you might think that the star of an M form has to be an M form, but really that doesn't quite follow from the rest of these things. So let's say the star of an M form, let's say that it's an f of M form, and we want to determine what f of M is. So from this condition, we find that f of m has to satisfy f of m plus n is equal to f of m plus f of n. And then from this condition, we find that f of m has to be equal to m, which is really telling you that f of m is plus or minus m. And this sign here is another sign that appears in non-commutative geometry. It's the sign epsilon double prime. Okay, so this, I'm going to call this sign epsilon double prime because it's going to be exactly identified with the sign that usually you see that defines the relation between the chirality gamma and the real structure J in non-commutative geometry. Okay, but so in other words, this is an important thing to keep in mind, that when you have a differential graded star algebra, there's really these two natural possibilities. In the one you're more familiar with is the epsilon double prime is equal to plus 1 case, where the star of an M form is an M form. But then there's this other case, the epsilon double prime is equal to minus 1 case, where the star of an M form is a minus M form. Okay? And, okay.
You have built in the modulo 8, because in non-commutative geometry, all those epsilons are valid modulo 8.
Right.
So you have a modulo 8 built in this, at which level the modulo 8?
Well, it is true. So here we just have these two signs so far. So there's only going to be 4 possibilities. And those are going to correspond to the 4 possible even dimensions modulo 8.
Okay.
at the end of the day, when I want to say, oh, there's such and such a KO dimension corresponding to this, then I can only tell you the value of that modulo 8.
Okay. And then you tell us the -1 form, what they are.
Yeah, exactly.
I still.
Yes, exactly. Yes, that's right. That's the
So -m forms.
minus m forms, yeah. In fact, we'll only ever have -1 forms, but sorry about that. Okay. Well, this is I want. Oh, sorry. Yeah, that's a notational screw up. At first, okay. So in most of the lecture, what I mean when I say A with no hat, that means the algebra of forms over A hat. Here, I wasn't thinking, and I just used A to denote a generic algebra. I was just going to tell you the general properties of any old differential graded star algebra. But in particular, we're going to apply those properties to B and A. Both B and A will be that. We'll satisfy those properties. Okay, so now can you guys see in the shadow here, or should I write? Okay, so now I just want to briefly review an idea due to Eilenberg originally back in the 1940s. He wanted to study the representations of non-associative algebras. Now, I should say we're not going to be interested in non-associative algebras here, but anyway, but the idea was there was a question of how do you define the representation of an algebra when A is non-associative, and his answer was, well, you can really define it to be a new algebra B with product given by, so if I consider two elements here. And I take the product of B times B prime and just expand. Oh, sorry. Then normally when you represent an algebra on H, what you're specifying, well, if you give a left representation, you're specifying a bilinear product of the form AH, which is in H. And if you're giving a right representation, you give a bilinear product, which you usually write HA, which is also in H. So imagine I give two bilinear products like that. Then that defines this algebra where, so in other words, this term is in A, this term is in H, this term is in H, and I set this term to 0. Okay, and then that's the idea of this approach is that then all the additional requirements that representation satisfies become re-expressed as associativity conditions on B. So if I now demand that this algebra B is associative, then that means that all the associators I can think of have to vanish. And so an associator that has three A's in it, AA prime and A double prime, that ends up telling me back that the algebra A is associative. But then these other associators that I can think of, like A times A prime times H, well, that's secretly telling me the exact same thing as the usual statement that pi of A times pi of A prime is equal, the usual definition of a left representation. And similarly, the associator with H all these things are 0. I'm demanding that the algebra be associative. Sorry, thank you. So this guy is similarly telling me that A is right represented on H in the usual way, And then there's one more non-trivial associator, which is this guy, which tells me that the left and right is really telling me that the left and right actions commute with each other. In other words, this is what would normally be called the order 0 condition in non-commutative geometry. Okay, so now the idea is that that was just a reinterpretation of, if you just have an ordinary algebra, you can re-express what it means to represent that algebra on H. You can re-express it as defining a new what we'll call Eilenberg algebra B, really a square 0 extension of A, and demanding that it be associative. Demanding that it share exactly the same, demanding that just this algebra shares the same property that this algebra does. Okay, so all we're going to do is the exact extension of this. We're just going to say, okay, if A is if A is the algebra of forms over A hat. So if A is in non-commutative geometry, A is going to be a differential graded star algebra. Then we want a corresponding differential graded star representation of that on H. Well, that turns out to still be neatly encoded just by the statement that the new algebra B is also a differential graded star algebra. Okay, so what I want to tell you then, the idea of how to apply this to non-commutative geometry is just that. What's the best way to do this? Can I avoid erasing for a little bit longer? Do they not move 2 at a time? They don't move? Oh, I think I screwed this guy up. All right, thank you. Okay, so the bottom line is that I want to quickly tell you, just to finish off the sort of formalism portion, I just want to tell you, I've sketched the basic idea, which is that I want A to be the algebra of forms, and I want to represent it on H. I want to take Eilenberg's perspective that that's a new algebra B, and I want to get back all of non-commutative geometry plus some more constraints by demanding that B is a differential graded star algebra. But I have to tell you in a little bit more detail exactly what A I want to take and what representation on H I want to take. So for A, suppose A hat is my algebra of coordinates, then I'm just going to form A as the universal algebra of differential forms over A hat in the usual way. So I'll take all products built from A's, but also built from the formal symbol D of A hat, and but then also all guys of this form. Okay, so normally when you define the universal differential algebra over A, so the universal algebra of differential forms over A hat, you take all products generated by A hats and symbols of the form D of A hat, modulo some conditions, modulo the fact that this guy is linear and satisfies the Leibniz condition on the A hats. And normally, when you're promoting this thing to a star algebra, you do so by assuming that this thing is not independent of this, that you assume some condition like this, that the star of a one form, in other words, you start with a star algebra here, but you want to end up with a star algebra here. So this object is already equipped with a star, but this object a priori is not, and we have to define what we mean by the star of this guy. So one possibility is to define it like this. Okay, and that's what's usually done. But that is really only that's really only a consistent thing to do when epsilon is +1. Okay, so that's not what we're going to do. there's a more general thing you should do, which is, okay, well, first of all, start by we're just going to take them as independent, okay? So I'm going to generate all products of these dudes. Okay, so for example, there's an example of a term in that algebra. So when I'm counting up what kind of form this is, it depends now whether I have epsilon prime is equal to +1 or -1. You know, if epsilon double prime is equal to +1, well, this is a 1 form, and then the star, when epsilon double prime is +1, the star of a 1 form is also a 1 form. So this is a 1 form, this is a 1 form. This whole form is a 2 form in that case. But when epsilon double prime is equal to -1, then this is a 1 form, but this thing is a star of a 1 form, so that's a -1 form. So this whole object is a 0 form, okay, in that case. Okay, so when I'm doing my accounting of what the grading is, did someone just say something? No. When I'm doing my accounting of what the grading is, I have to remember that. So anyway, so I generate, but other than that, I generate the algebra in exactly the same way that I do for the ordinary universal algebra of differential forms. Then when I want to promote, you know, there's a step in the ordinary construction where I want to promote D from an operator on A hat to an operator on the whole of A. And normally, I do that by just declaring that even though previously I was just regarding it as a symbol that acted on elements of A hat, I'm going to let it operate now on. I'm going to expand it to operating on any element of A, any arbitrary M form or N form, by 1, taking it to satisfy the graded Leibniz condition on the whole algebra, and then 2, taking it to satisfy this property, that D of A is 0. That would normally be it in the normal construction, but again, we're doing this fancier starred version of the normal construction, so we need one more condition to make the whole thing close, which is that D of A star is also equal to 0. Okay, so that's going to be a new condition in our formalism. Okay, but that maybe went a little bit fast, but that's the algebra A. Okay, the bottom line is that for any coordinate algebra A hat you choose, I'm going to construct the algebra of forms, the universal star algebra of differential forms this way, which is not going to force me yet to choose between epsilon double prime is equal to +1 or -1. These two fundamental cases. And now for the representation on H, well, I want to take a graded representation of A on H. I mean, I have this differential graded algebra. I want, at the end of the day, a differential graded representation. So I'm going to take the simplest one I can get away with. The simplest non-trivial possibility is to have the representation space have only 2 non-zero components. And so I can just call them. I can just call them H left and H right. Now, if you think it through, there's really going to be 2 possible ways to assign the grading to these things. So in the epsilon double prime is equal to +1 case, the gradings here will be 0 and 1. But in the epsilon double prime is equal to -1 case, the gradings will have to be -1/2 and 1/2. Okay, so you know, you can, there's a sense in which there are these two, you know, there are these two ways that a fermionic two-state system shows up in physics. It either shows up as a Fock state, where each state can either have 0 or 1 fermions in it, or the other classic way you encounter a fermion in a two-state system is a spin 1/2 particle, where the labeling is where the labeling of the two states is +1/2 and -1/2. And in some sense, that these two possibilities correspond to those two different possibilities. Or in any case, that's at least a mnemonic that's helpful to distinguish them in your mind. Okay, and so you know, so let me see. The thing I wanted to say next was that. Let's see. First of all, I want to define. So I picked a star algebra A hat. I created a star algebra A, and now I'm representing that on H. And again, by Eilenberg's logic, I'm trying to form a combined algebra B so that B has all the properties that A had. The zero-order extension has all the same properties as the object it's representing. So this was a star algebra. So this guy needs a star operation. And so the star operates. So in other words, H will have to be equipped with a star operation. And that's just what I'll call JH. Okay, so J enters in this picture as it's just the name of the operator that encodes how the star operation acts on the Hilbert space. And then finally, I had a differential on here that I want to extend to a differential on the whole of B. So I apparently have to have a differential that acts on H. And I'll just define that. That's some operator from H to H. I'll call that little dh. And it, well, because of the grading, it has to look like this. It has to be upper off diagonal, have some non-zero component delta, and then everything else is going to be 0. Okay, so then this is really all I need. You know you know, what I want to emphasize is that there's no freedom really to monkey around. You choose this. Now, there's two places where something can be input. You get to choose whatever initial algebra of coordinates A hat you want, and then you also get to tell me what is the left action of A hat on H. In other words, what is pi of A hat on H? How do zero forms act? But then everything else about the formalism is then determined. The formalism is extremely constrained by the statement that then the B that I construct is a associative differential graded star algebra. And so in particular, okay, for example, we can, you know, one can go through and find the you know, how the so once you pick how a zero form acts, once you tell me pi of A hat, so how does a one form act then? Well, so here, you know, you find something a little bit different than normal non-commutative geometry. You find the differential graded structure of B demands that the left action of a one form on H is the commutator not of big D, not the Dirac operator with A hat, but little d. So it's going to be a guy like this with an off diagonal that again is upper off diagonal. And okay, and in fact, you're also going to find that the right action of dA is also upper off diagonal. So left action of dA and right action of dA are always upper off diagonal, but the left action of dA star we still have to work out. So again, Fidele, sorry, yes. So again, this is the left action and right action of a 1 form. Now, you had asked about what the -1 forms were. Again, so first of all, the -1 forms just formally are the stars. They appear in the construction of A, the universal differential algebra, as just coming from the fact that I have these operators dA star floating around in addition to dA. And if I build those up, I build up a more and more negative form. But then what is the difference between representing a 1 form and representing a -1 form? So that's here. So what you find is that you find that if you represent a 1 form or a -1 form, that what you get depends on the sign of epsilon double prime. So in the case where epsilon double prime is +1, well, you know that in the case where epsilon double prime is supposed to in the case where epsilon double prime is +1, dA star is supposed to be a 1 form, just like dA. And indeed, you find that just like the 1 forms were upper off-diagonal matrices on our 2-component space, the left and right action of the star of a 1 form is also an upper off-diagonal matrix. So that's what happens when epsilon double prime is +1. But when epsilon double prime is -1, you get a lower off-diagonal matrix. Okay, so that sounds like a detail, but that's actually the key to resolving one of the puzzles. That's our way of resolving one of the puzzles that Bruder et al. Solved a different way. Remember, I said that there was, in our old formalism, we got these new second-order conditions, second-order constraints that were demanding that, the 0th order constraint says the right action and left action of a 0 form commute. The 1st order constraint says that the left action of a 0 form commutes with the right action of a 1 form. The 2nd order constraint says that the left action of a 1 form commutes with the right action of a 1 form. And we said that worked great for the finite space, for the 6-dimensional finite space, but it was too strong on the 4-dimensional continuous space. But that's resolved here because it turns out that the 2nd order condition, this business, So what you find is that, oh well, I'm getting ahead of myself here. Sorry. So maybe I'll get to this in a moment. But what you find is that any second-order condition like this, where you take the associator of a 1 form with a Hilbert space element with another 1 form, well, that's always 0. And similarly, if you take dA star with H with dA star, that's always 0. But now, a thing that is not always 0 is a thing that's non-trivial is the associator of a left action of dA with a right action of dA star. Okay, we have to demand that that's 0, but that only gives a non-trivial constraint when epsilon double prime is -1 because of this structure. So, in other words, it's automatically the case that you maintain the success of the previous formalism. You maintain this exact same second-order condition that you used to get on the finite space, which was good. That gave this successful constraint that I'll describe more in a moment. But the over-constraint on the continuous part that we used to get, that just disappears. There is no non-trivial constraint on the trivial part. There's no non-trivial second-order condition when epsilon double prime is +1, which is the case for the 4-dimensional continuous space.
Why have you written that the right action and left action are the same?
Sorry, they're not the same. I just meant to say they're. Sorry, apologies. I meant to say they both have the same basic form.
Oh, the matrix.
Yeah, the same blocks are non-zero. Yeah.
So a -1 form is represented as a lower diagonal matrix.
Yeah.
And so if I multiply a 1 and a -1,
Mm-hmm.
I get something which is on the diagonal.
Mm-hmm.
However, it depends if I do right -1 times 1 or 1 minus times 1, in which order I do, I get something which is only in the upper diagonal or in the diagonal in the 1-1 position or 2-2 position.
Yeah. Mm-hmm.
Okay. So I have sort of two different scalars.
Oh, that's quite true. Yes, exactly. So that's true. The zero forms in the algebra A are bigger than just A hat. It's not just A hat. But that's totally consistent. There's nothing inconsistent with that, and the whole nothing that's inconsistent with nothing. But that's a good point. Okay, so I just want to sketch. I blame the airplane and the jet lag for the fact that I'm behaving like such an idiot with the boards. Okay, so let me just very briefly sketch. So from demanding, so I told you how the algebra B is defined. Now we want to demand that it's a star DGA. And what do we get back from that requirement? From the vanishing of the associators, all the different associators we can think of, we get a bunch of things. We recover the fact that A hat and A, the assumptions that those things are both associative. We get back the fact that pi of A is a left representation on H. And we get back the fact that pi of A naught, this guy, that the right action, we get that the left action is a representation in the usual sense, and the right action is a representation of A in the usual sense. And then we get the order 0 conditions from associativity, and the order 1 conditions, and then these new order 2 conditions.
Wait a minute, where does the Dirac operator come from?
Yeah, we'll get to that in a second. So
We need that before you even say what order 1 condition.
okay, that's a fair point. That's a fair point. So the order in this way of doing it, we're just going to define. We have this two-component space on which there is this operator, the operator little d acts. So the representation of little d on H is this guy that I've been writing this way. So capital D is just little d plus little d star. So that's quite a good point. And of course, that's very natural. Again, from the standpoint of just like you normally think of D as being D plus D star. That's also what it is here. Okay, and then from but there's these new order 2 conditions. So so as we're cataloging what comes out from requiring that B is a star DGA. I'm just saying there's various assumptions that you know and love from non-commutative geometry, and then there's this one new guy that all come from associativity of B. From the fact that B is a star algebra, you get another bunch of things that you're familiar with. You get the assumption that A hat is a star algebra. You get the assumption that A is a star algebra. You get the fact that H is equipped with an antilinear operator J. You get the fact that J squares to plus or minus 1. You get the fact that the right action is related to the left action by the usual formula. And then from the fact that it's a differential graded star algebra, you get the fact that, okay, so again, because I have this two-component space, without putting anything else in, I'm just free to define, to make contact with usual notation. I'm free to define this operator D as just the sum of little d and little d dagger. And I'm also free to just define the operator gamma on this space, which is just minus, I have this graded space, and so I just can define this operator that detects that grading. And so from the DGA structure, then it follows, it's now a consequence of the fact that B is differentially graded, that D and gamma anti-commute, that the left action and right action of zero forms commute with gamma, that J and gamma commute or anti-commute depending on the sign of epsilon double prime. Because it's just a space with two components, d of a hat is automatically 0. That's one new condition, but it's trivial. But then there's this other new condition I mentioned before, that d of a hat star has to be equal to 0. And that guy is a new non-trivial condition. So again, I've boxed the two new non-trivial conditions that arise. Okay, so now let me say quickly how this. Have I already run over my time? No. It's amazing. But I'll get there. No, I'll try not to. Okay. Is anyone still following? Do you guys have any questions? What's the rate? We have like 20% or something like that. If John Barrett is following, that tells me nothing about the rest of the audience. This stuff would be.
Look, if I follow at least in terms of mass, this helps a lot.
Okay.
If you want to count masses rather than heads. I follow
all right. Well, I'll focus on. Okay. Oh no. Okay, so finally, I just want to quickly describe the application to the traditional standard model geometry, how this all looks in that language, or how that all looks in this language, I should say. So again, that was all defining the category of algebras that are relevant for or the class of algebras, I should say, that are relevant for describing non-commutative geometry. But now, remember, to fix a specific algebra, I just have to tell you two things. I have to tell you what is the specific coordinate algebra I want to choose, and then what is the specific left action of the zero forms of that algebra on the Hilbert space. And so then for that, I'll just take the example where I take the sort of the traditional, the original guy that was used to describe the standard model, where we take C plus H plus M3C. And we take the left action. I'm not sure it's worth writing this out exactly, but just in, it's probably not worth writing this out, is it? Well, okay. I don't know. Somehow, maybe it'll help somebody to see something on the board. Could be too abstract if I don't do this. Who's with me? Should I write this out or no? I'm halfway there already. If we just stop talking about it, then we'd be done already.
Raise it, I will appreciate it for the next seminar.
The what? Oh,
If you write it and don't erase the blackboard.
okay, yeah. Okay, there's this famous formula. that turns out to capture so much about the standard model so beautifully. And so, you know, if okay, and so then we have this is acting on some Hilbert space of fermions. I'm just writing out the finite part of the geometry here, just to focus on that for the moment. And okay, so here this is acting on some leptons and fermions. Some leptons and quarks, and with right-handed indices, you know, there's 8 possibilities here, and that's lepton and quark times left-handed, right-handed times particle and antiparticle that are distributed and appropriately along that column and acted on by those 8 blocks. So the Dirac operator if you take the ordinary non-commutative geometry constraints on this guy, so the ones that are usually present, that D is so these various conditions in the first order condition, those constrain delta to be this matrix delta to be of this basic form and then the whole thing is symmetric. So there's some okay, where M is a 2 by 2 matrix like this, with a 0 component, but then these two non-zero parameters in it, and then N is a sort of 6 by 2 matrix with non-zero 3 vectors C and D in it, and so really all of these parameters. These are extra parameters. We want to keep A. A will be the sort of Majorana-like Yukawa coupling between the right-handed neutrino and itself, and potentially a scalar field. But these coefficients B, C, and D, we want to set those to 0. Those give rise to unwanted Yukawa couplings and unwanted scalar fields in the theory if they're non-zero, phenomenologically unwanted. The usual way that that's dealt with is by adding a new condition, the so-called massless photon condition, which has the effect of setting those extra unwanted terms to 0. But now we have these new conditions. We can ask what they do. So it turns out that the new second order condition again, this second order condition is non-trivial because in the finite space, epsilon double prime is -1. That's something I hadn't told you yet, but if you've looked into this standard model construction, you may know that that's true of the 6-dimensional finite space in the standard model. So there's this so in that case, in the finite space, there's this non-trivial second order condition, and it has 4 possible solutions. It turns out, and one of those solutions is exactly to set to 0 the terms that you want to set to 0, and then there's these 3 other solutions. Which so it gets you down to 4 cases, one solution is the right one. So then to go a little bit further, let's assume. Okay. So to go just a little bit further, I want to now assume that the operator dh dagger, or in other words, that the operator d squared, the Dirac operator squared, I want to assume that that's non-singular, okay, that has non-vanishing determinant. Okay, so it turns out that of the four, if I take that assumption, that it's just sort of that this operator is generic in that sense, that's enough to select the first of the four solutions, the one that I want phenomenologically. But I just want to pause to say, you know, it's kind of interesting in this approach that there's another interpretation to what's going on here, which is that, you know, we already saw that the two-component that when we think of H as this graded two-component Hilbert space, you know, it's a kind of two-level set of fermions, which either is labeled 0 or 1, like in a fermionic Fock space, or minus a half plus a half, like in spin 1/2 system. And then acting on this space, we have these basically raising and lowering operators, dh and dh dagger, which are very parallel to which are, you know, strongly analogous to the fermionic creation and annihilation operators, which also, you know, these guys are upper off diagonal or lower off diagonal matrices that just bump you up or bump you down, just like the normal fermionic creation and annihilation operators bump you up and down in a two-level fermionic Hilbert space. And you know, just like these guys satisfy these commutation relations, AA dagger, that A anti-commutes with A and A dagger anti-commutes with A dagger. These guys also satisfy that D anti-commutes with D, and D dagger anti-commutes with D dagger. And you know, it's interesting that the one other condition that you take here, which is that A anti-commutes with A dagger to give 1, you know, the parallel condition here is this, that D and D dagger anti-commute to be non-singular, which selects the one of the four solutions that you want here. And then furthermore, well, Shane, you're going to have to. I don't really have time to say this, but the other condition here, the other non-trivial condition, turns out to say that what had previously been an arbitrary 2x2 matrix here, these two arbitrary 2x2 Yukawa coupling matrices, they're not arbitrary. They take the form that corresponds to having just a single Higgs boson. Okay, they have some particular form here. Oh well, I'm out of time. I don't have time to really write this. The bottom line is that it works great. You know, that's really what I want to say. To summarize, it's a way of rewriting the non-commutative geometry so that the basic object is this algebra B, which is a simple superalgebra. Seriously? I guess that means we. Oh, really?
This is, don't worry, it's standard, first Monday of the month, 12 o'clock.
Okay. So I'm glad that woke you up. I just want to say two sentences to summarize. The basic object is this algebra B. It's this nice superalgebra with the property that if you building it was very natural. It was just the natural definition of the algebra of forms, and then the simplest possible graded representation of that thing. That's what B is. Demanding that it is a differential graded star algebra recovers nearly the entire list of normal axioms and assumptions of non-commutative geometry, but it gives you a couple extra conditions, non-trivial conditions. And those conditions now really work beautifully when you actually apply them to the traditional geometry used to describe the standard model. They eliminate the need for the massless photon condition, and they give you the other thing I didn't get to describe was they give you this equation, which is exactly the normal equation describing the structure of the remaining unbroken U1 after, anyway, I leave it to Shane. But anyway, yeah, that's what I wanted to say. So the paper's on the archive tonight. Shane, we're here all week.
Yeah, so you said you fixed your problem with manifold at dimension 4 because epsilon double prime is 1.
But in Lorentzian signature, it's not. Is that what you were going to say?
Well, actually, no. I was going to say, are you still in trouble with manifolds at dimension 2 or 6?
Yeah, as far as I know, yes.
Oh, so they're ruled out.
Well, that's right. I mean, in this way of doing it, I mean, you know, there's physicists and there's mathematicians. You know, I like it if the only thing that fits, if there's a neat formalism and the only thing that fits in is the physically observed thing. For me, that's great. I'm not distraught at the fact that it doesn't admit all sorts of more general stuff that we don't see. I mean, that you can still define formalisms that describe all that stuff, but I like that the idea that this zeroes in on what's actually what the physics is about.
Okay.
Yeah.
Can you give an example of a form of -1 degree explicitly here? It's a commutator of D with what? With J and J?
Yeah. So in general, what it is so as I say,
No, you can erase.
So you can use the DGA structure to determine that the left action of an exact one form is the commutator of little d. So whatever this matrix little d was, it's the commutator of that with the left action of A. But you can similarly, in an analogous way, work out what is the left action of d of A star. And it is given by, let's see, what is it given by? You know, it turns out to be J times the commutator of d of H with the right action of A times the operator -1 to the order of H. This thing you might not be familiar with seeing, but this is because H is now this graded space, and the two components of H left and H right, have different gradings in our approach. And so to get the differential, to get the Leibniz, and that is true. Well, it depends. It depends on whether you're in signature. It depends on what the sign of epsilon prime. And then J inverse. Okay, and so now if you take this in the case where epsilon double prime is -1, then this matrix looks like this with an upper off-diagonal bit as the only non-zero bit, whereas this matrix looks like this with a lower off-diagonal bit.
Did you say that you wanted only one X?
Yeah.
One X. One should agree with nature. Apparently at CERN they have seen a bomb
At 750.
It has already at least 20 different explanations.
That's the most likely one.
Huh?
Now. Sure.
More Higgs? There are more Higgs?
But that's not.
If that is ever promoted to an actual, if that is promoted to a detection, then no doubt I and everybody else will have some thinking to do. That's definitely right. Yes, that's true. I don't yet. It's not 5 sigma yet. I'm still allowed to live in a naive land in which there's only one Higgs boson.
You could work with a larger algebra.
Yeah.
No, but really, the problem is that you run the risk not of having more than 1x. To have 1x for each you have a couple.
Which you don't get here.
Which you don't get it. now you can fiddle and get 2 X's, but certainly we don't have an X. So the field that gives mass to particles is 1. There is not one field for each particle. Now you can have a 2 X because of the breaking pattern or something, but the good thing that you get here is that you get one universal X. Can be bi-universal, but not 16 different.
So does your 1 Higgs result still hold if you have 3 generations?
Yeah.
Does that need the mixing to be non-trivial, or is it independent?
Does it need the mixing to be? So the reason that happens is because it's the same argument about why. I mean, I might not be understanding your question, but so so that where did it go?
Yeah, so why is the Higgs the same in all 3 generations?
So yeah, so this equation ends up giving you know, what happens is that you get, when you expand out this equation, you get the exact same equation for the y sub L and y sub Q, and for each component of y sub L and y sub Q, if they're 3x3 matrices. Sorry, if they're promoted to a 3-generation structure. So you end up only having the freedom for each set of those equations to choose, you know, 2 free Yukawa couplings, and you get a choice for each component ij. You get an independent. You just get a decoupled set of equations like that for each I and j of the 3x3 ij family matrix. And so you just get to choose 2 different free parameters as a solution for each one. But you don't get to choose an independent phi1 and phi2 for each one. And that's not a very good explanation of how that happens. So what I mean to say is that, well, that's exactly how much free parameter there is in each equation. There's a freedom to the equations break up in such a way that you can divide out a common factor from a given set of equations. But then once you've done that, you have the same equation, same restriction for each different I and j. And so the solution to that is some particular phi1 and phi2, some particular Higgs field. But you don't get to choose a different solution for each I and j. Yeah, you know, but the better thing is if we just look at the equations right afterwards. But it definitely is true that there's just 1 Higgs, but it just gets promoted to.
Right, let's postpone further questions to during the lunch break. Thanks
Okay.
again.